In this online lecture, we're going to discuss UV spectroscopy, and what we're going to see is that UV spectroscopy, or the UV spectrometer, the actual machine, detects whether or not we have a conjugated system or not. Okay, that's really its function. So in order to understand it, let's go back, let's get a little review of conjugated systems. Here's a conjugated system, the most simplest one. And remember, conjugated systems are simply alternating double, single, double bonds. Sometimes they're triple, single, triple, right? Triple, single, double, okay? Just alternating multiple bonds, all right? So this is the most simple conjugated system. And let's remind ourselves what's happening at an orbital level here. Remember, each one of the carbons in the conjugated system is sp2 hybridized, and that means that each one has an unhybridized p orbital, and each unhybridized p orbital has an electron in it, and those electrons are sideways overlapping to make that pi bond. Remember the truth behind that pi bond. Every pi bond is two p orbitals sideways overlapping. So that means the pi bond on the right here, same thing is happening. Two p orbitals with electrons are sideways overlapping to make that pi bond, which means that one way to represent a conjugated system is simply by just saying this, using molecular orbital theory. Remember, these dashes become orbitals like that, right? And so what we're saying here is we have 4 total p orbitals, and each one has an electron in it. And molecular orbital theory, remember, electrons become these little half-headed arrow things, right? So here's what I want you to think. A conjugated system, that system above, could be just easily as represented as that structure or that thing, whatever that diagram is below, okay? So below, that's the essence of every simple conjugated system. 4 p orbitals, each with an electron in each orbital, okay? So let's work with that then. Again, here's our conjugated system, one way to think about it. Now remember, in molecular orbital theory, if you remember from Organic Chemistry 1, it basically said that electrons, remember, could be waves or particles. And molecular orbital theory, remember, treats electrons as both wave and particle. Okay. For a review on that, make sure you see molecular orbital theory, that online lecture. Okay. But if you remember that, if electrons could be waves, then basically molecular orbital theory said that if electrons are waves, there's technically 4 ways that these electrons could meet up. Okay, one way is through what's called a sigma bonding molecular orbital, and that's this. It means that if the electrons are treated as waves, all those 4 different waves, those 4 different electrons, are all plus plus plus, right, and all negative 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 negative, like that. That's one way the electrons could meet up, meaning all the electrons are in the same exact phase when they meet up, all plus. That's one way. But remember, there's another possibility that these electrons could meet up if we think of them as waves, and that's this way. The 2 left-hand ones are meeting up plus, and the 2 right-hand ones are meeting up with the pluses below, okay? So if that's one way they meet up, that's actually called, they term that the pi bonding molecular orbital. And what I'd want you to know here, some vocab, is we'd say that this right here is a node, okay? That means that there's 0 wave displacement right there. So we could just memorize that. The pi bonding molecular orbital has 1 node, all right? However, there's a third way that these electrons could come together as waves, and to represent that third way is this possibility right here. This is different, right? It's distinct from the first 2, but notice in this possible way that the electrons meet up, we end up with 2 nodes, okay? And we term this way of meeting up, we call it the pi star bonding molecular orbital, or the anti-pi bonding molecular orbital. However, there's one last way that these electrons could come together, one final way. They call it the sigma star bonding molecular orbital, or the sigma anti-bonding molecular orbital. That's this way they meet up, okay, that possibility. Notice in this possibility, there are 3 nodes that are formed, okay? Also here, remember, we're not just listing 4 possible ways, but we're putting them in order of increasing energy. In fact, energy increases as you go up. So the first possible way they could meet up, remember all plus, the sigma bonding molecular orbital, that would be the lowest energy situation. Okay, how do we know that? It's hardcore quantum mechanics. It's beyond organic chemistry. We just have to accept that that's the lowest energy situation. Okay, now remember, if you remember how this worked, molecular orbital theory, what we did is we took the atomic orbitals here, right, the electrons in the atomic p orbitals here, and we use those electrons to fill this chart right here. Okay, and remember, we fill it by energy. We go from low energy to high energy. So again, remember, we have 4 electrons in the atomic orbitals to work with. So let's say the first one would go here in the lowest energy. The second one would be teamed up with him like this. Remember, at most 2 electrons can fit in any orbital. So where do the other 2 go? Well, we'd have to move up 1 energy level. So the next one would go here. That's the third one. And the fourth one again would be doubled up like that. Okay, and just some terms here. Let's get some vocab down. We call that second situation the HOMO, okay, which means highest occupied molecular orbital. What does that mean? Highest occupied by electrons. That's what they mean. The highest orbital, meaning in terms of energy, the highest energy orbital that is occupied by electrons. And we would call the pi star bonding molecular orbital right above the HOMO, he's termed the LUMO. Okay, he is the lowest unoccupied molecular orbital. All right, so he's the lowest orbital in terms of energy that doesn't have electrons in it. All right, so here what happens here is this basically. This becomes yet another way to characterize our conjugated system, right? That diagram is basically, like I said, a way to describe a conjugated system. So if this is what's going to help us understand how the UV spectrometer works. Remember, all of these machines, we have to understand, number 1, how the machine works, and 2, how to read the data. For this machine, we're going to see it's harder to understand how it works, but easier to read the data, all right? But if you followed me so far, you're going to be able to understand this machine, okay? So here's what happens. Again, what we see here on that diagram that you see there on the right in front of you represents a conjugated system. Now here on the left, I'm going to say, let's say we have a UV spectrometer, and let's say we put this molecule in it. Okay, clearly this molecule is not conjugated. What happens is we have a UV light, let's say like a flashlight, and this flashlight has the ability to shine all UV lights, all the different various frequencies and wavelengths of UV light. So if we take that machine right here and we put a detector right here on the other side and we shine all the different types of UV lights, that UV light will go right through our molecule, and the detector will say, bing, I detected that light, okay? Which means no UV light would be absorbed, all right? But, however, let's say, again, this time in the machine we put a conjugated system, and this time we shine all different types of UV light at it. What's going to happen is the molecule will actually absorb that UV light, all right? We need to understand why. Why do conjugated systems absorb UV light? All right, well, here's why. Let's take a look at that here. Remember, it's going to take some physics equations here. Don't let that discourage you, though. But remember, in terms of physics here, you had an equation that said the energy of light is equal to Planck's constant, h, times the frequency of light. Remember, there's also this equation too, the speed of light is equal to lambda, wavelength, times frequency. Now, if I plug in this bottom equation into the top equation for frequency, I end up with this expression right here. So using a little algebra, take my word for it, we can say that the energy of light is equal to Planck's constant times the speed of light divided by the wavelength of light. Okay, so there it is. That c, remember, is the speed of light. So think about it. That's a constant. The speed of light is constant. Remember what else is constant? H. H is Planck's constant. That value, these two values don't change. However, it's lambda that can vary. Different lights have different wavelengths. And those wavelengths right here, remember, UV wavelengths, they're around 190 to 300 nanometers, okay? If you are a light wave and you have a wavelength that's between 190 and 300, you're considered UV light, okay? So that means that UV light has a certain lambda wavelength which corresponds to a certain amount of energy. These UV waves have certain energies associated with them. And it just so happens here that the difference in energy between HOMO and LUMO, that right there, those energies, that difference in energy from HOMO to LUMO corresponds to the energy, those energies that that UV wavelengths have. So what am I saying here? What does this all mean? Let's go back here. Again, we shine various UV lights, right, with certain wavelengths at our molecule. Remember, the conjugated system will absorb light at UV wavelengths. And remember, we were trying to figure out why that's so. Well, remember, what happens is one of the electrons here in the HOMO gets knocked up here to the LUMO, all right? And that's why that conjugated system absorbs UV light. It's simply because the difference in energy between HOMO and LUMO is equal to UV light energy. So that's why conjugated systems absorb UV light. Here's some vocab. We call that something. We call that a pi to pi star or pi to anti-pi transition. So now let's talk about how to read the data. Okay, so let's go back here. Remember, if we stuck a non-conjugated system molecule here in our UV spectrometer, we will shine all the UV rays at all those wavelengths, and it'll go right through the sample and hit the detector. And what happens here, the machine spits out this basically. On the x-axis, or actually the y-axis here, we have absorbance, all right? And on the x-axis, we have the wavelengths in nanometers for UV light, okay? And since the detector detects the light, it basically says there was no absorption, right? Your molecule absorbed none of the light. So you'd get a flat line like this, okay? However, though, if we stick a conjugated system and we shine all the wavelengths of UV light, we will get some absorption, okay? And here's what the machine would spit out. Here's the data. It would look something like this, okay? Remember, now the conjugated system doesn't absorb every wavelength in the UV region of the electromagnetic spectrum. It absorbs at what's called a lambda max, okay? But that's all that matters, is if we get an absorption anywhere at these wavelengths, we definitely have a conjugated system. So this is kind of like, we see this as a positive sign that our molecule is conjugated. Here then, one other thing that we should know, one other aspect is that there's an equation that relates to the UV spectrometer, and that equation looks like this, and it's called, I'm not kidding, seriously, it's called the Beer-Lambert law, okay? Basically, what this equation calculates is you plug in the absorbance, right? Remember, that's off the chart. Remember, on the y-axis of our spectrum is absorbance. You can plug in absorbance right there. Here, you could calculate what's called the molar absorptivity, which is epsilon or E. Here you plug in the concentration. That's the concentration of your sample. And L in the equation right here is just your path length. That means for your specific machine, you see there on the right, on the left-hand side, that arrow, that green arrow there, that's the path length. How far does the UV light have to travel to get to the detector? That's what you would plug in here, okay? You wouldn't have to know this equation for the MCAT, so please don't memorize it, but just at least understand what would be plugged in where.